talk about today. I love this. Okay, so let's see. MP7 is in your hands at this point. I feel too loud. So I looked at the due dates, and I was surprised that it's actually due kind of significantly before the end of the semester. So I will not be the least bit surprised if the due date for this slips a little bit, especially given that MP6's due date slipped a day. So while I'm not making promises, I will make an announcement very shortly with updated due dates. Wade, will you remind me at the staff meeting to bring it up? The MP7 due date is on the staff meeting for tonight. Okay, so I think probably that's, what is that? A lower bound on the amount of time that you have. Okay. All right. We were talking about a brand new abstract data type, loosely referred to as the disjoint sets, ADT. It's also sometimes known by the structure that supports it. So at the end of the day, you'll have another name for this thing. And another observation to connect it to something you've done before is that it is oftentimes the ADT that you use to maintain equivalence relations, okay? So what's an equivalence relation? It's just a collection of disjoint sets, and by sets I mean the mathematical notion of sets, where everything in a set is related to one another under the equivalence relation. So for example, if the equivalence relation is described here, it's over the collection of people in this room, or the set of students in this room, aka the domain of the equivalence relation, then everyone in each of these sets would have the same favorite among these handheld video games, okay? Now, I can draw a picture of this equivalence relation by taking an element from the domain and creating a node labeled by that element, and then drawing an edge between two of these elements, or two of these nodes, if they are related to one another. Now, I want you to tell me what is the special characteristic, the special way of describing the graphs that are induced by these relationships. So this one looks like this, 2 and 5 and 9. Yeah? Yeah, so they have cycles in them for sure. Yep. What else? What else is true of each of these subgraphs in this? Yeah? Yeah, these are complete subgraphs. So this is a complete graph. And the reason for that is if I ask you which of these sets you would like to be a member of, which of those sets would you like to be a member of? Just point to one of them. This one right here. So if I were to add a new element of this set, I would be saying this guy, his favorite game is the same as everybody else's in that set, and so under the relation, I would draw an edge between him and everyone else. If there's an edge between every pair of elements in a set, we've defined a complete graph. So that's CS173 stuff, okay? Any question about that? Now, the equivalence class piece of this, the connection to equivalence relations, is that each one of these subgraphs defines an equivalence class of things that are all related to one another. All right, any questions so far about the setup here? So we've got this equivalence relation. It partitions the domain. In the example, it's the set of people in the room into these disjoint sets, okay? Now, another thing from discrete math that I want to remind you about is our way of describing these sets. the way we describe a set from the equivalence relation is usually with square brackets like this, and we call this an equivalence class. And it is designed, or it's defined to be the set of all things that are related to 2. Okay? And in this example, we could draw that out. We could say, well, the set of all things that's related to 2 are 2 and 5 and 9. Okay? So I'm just sort of spouting a bunch of stuff here, all of which means the same thing. So this set means the same thing as that graph, which means can be expressed this way and this way, all the same. Okay? Now, here's the part of it that when I learned this material, found to be very, very strange. This thing right here that we use to communicate the set itself is not deterministic. That thing right there is arbitrarily chosen, or an arbitrary member from this set. So in fact, while the notation changes, I could write this as a 5, the description of the set itself doesn't change at all. If I define it in set notation, it changes, but the elements of the set are no different. Okay? So by way of checking, how many different ways, how many different representatives do we have of this class? We have 2 because there are 2 things in the set. Okay? Now, the reason I bring this up here is because of the following. We're going to define an abstract data type on these disjoint collection of sets. And they behave very much like, the functions in them behave very much like the mathematical functions do. So I'm going to talk about that for just a minute right here. When I do a find on 4, it's completely different than find in the context of dictionaries. Find in the context of dictionaries is intended to find key 4 and then give me its value. Find in the context of disjoint sets finds 4 by telling me what set it's in. Okay, so the purpose of find is to tell me what set it's in. So the idea is, the way to think about this is that find returns the set 0, 1, 4, 8. Okay, that's different, right? It's more of a membership test. Furthermore, it gets even weirder because rather than return all the elements of a set, which might be kind of expensive in terms of memory and computation in general, rather than return all of the elements of a set, we're going to return some representative of the set. The representative gets returned. Okay? And you'll see how that plays out in a little bit. All right, so the way to think about find of 4 is as returning a set. But what's actually going to happen, what you're going to see in the interface, is that the find of 4 is going to return a special element of the set. Okay? All right. Is this true in our example? Is that true? Find 4 and 8 are in the same set, so this will return true. Yes, exactly. But look what constraint that imposes on our interface. It means that this representative has to be the same for both of them, right? So the implication of this, so this is true, and this means the representative for the set containing 4 has to be the same as the representative for the set containing 8. Okay, any question about that? Okay, so these are sets, right? So it probably doesn't surprise us that one of the fundamental operations that we want to do on the sets is to take their unions. So that's this next part. Now let's look at this code for just a minute. What I want you to do is think of an English way of describing that to me. What does this mean, the conditional? What does the conditional mean? If 7 and 2 are not in the same set, good, really good. So if 7 and 2 are in different sets, then, if they're already in different sets, we're going to take the union of their two sets, okay? It's just sort of an example of some of the things that we might do here, some of the questions that we might ask. And in fact, in MP7, you're going to be using conditionals of this type computationally in the solution to another problem. So that's a little bit of foreshadowing. So now let's talk about union for a minute. I want the union to have two sets as arguments. So I take the find here. I take the find here because it's going to effectively return to me a set, even though it just returns the representative, okay? And the same here. And that's because I want unions to have, unions act on sets, okay? The question is, what happens when we do this in implementation? Well, that's a matter of design. We're going to design what we want to have happen when we take the union of these two sets. Suffice to say, all we really want to have happen is we want to change the collection. We want to change the collection of sets so that there's one fewer set, right? Because we're unioning two together. And moreover, that one of them increases in size, or we replace two of them with one. So in the end, we want something that looks more like what you see here than what was originally printed, okay? Ask me questions. I'm done with this slide unless you ask me questions. I'm feeling very direct today. Ask me questions. Yeah? Okay, so find of 4 is intending to tell you what set find is, or what set 4 is in, okay? Now we could return to you the whole set, but that means I have to represent that set by all of its members, and that feels expensive to me. So I'm going to take advantage of this mathematical notion of equivalence classes and the way that we designate them via a representative to say, okay, I'm going to use representatives from sets to represent the set, okay? And that's it. So when I do a find of 4, I know I'm going to get 4 set, but not the whole thing, just the representative. I think it will become clearer when we do an implementation, okay, when we see how that plays out in implementation. All right, any other questions? Yes? So that's the freaky part, right? The way the math works is it doesn't matter which one goes here, right? It doesn't matter which one of the elements of the set we use to represent the set. That will still be true for us, but it also will not be arbitrary. We will be engineering the representative in the implementation, okay? So that's part of the large question of the implementation. Like, what should be our representative? How are we going to, what are we doing with our representative? Okay. On that note, are you ready to talk about, let's talk about the details of the abstract data type. So what we want in terms of data, is a collection of disjoint sets. Our implementation will determine what that collection looks like. You can tell that we're probably going to throw the collection into an array. Okay? So that's what the data looks like associated with the class. It's just an array. Let's see. Each set has a representative member. So we'll be able to ask an element, who represents you? I can tell your membership, I can tell your representation by querying it somehow, querying each set somehow. Then finally, we need a way to build a set given a single key. We need a way to take union of two sets. And here's the kind of interesting part, I think. We need a way to find the representative given a key. Okay? Now notice that our return value here is the same type of thing as our key, right? Just as it is in the math. We're going to return the same type of thing. Now, in every example that we see, all of those t's up there will be small integers. If you are in a situation where you want your keys to be something other than small integers, it will be your responsibility to keep a mapping between small integers and those keys. Because all of our implementations, our bad ones and our good ones, all of them will assume that our keys are the indices of an array. Okay? Any question about that? All right, so keeping track of what those indices mean and what those identifiers are, that's on you. You can keep a table. Maybe you can keep a hash table. All right, so a first data structure for disjoint sets. Assuming the keys can be used as the indices of an array, look what I did here. Can you see? Do you see how this collection of sets maps to this array? Do you see it? Yeah, I kind of arbitrarily chose one of the elements to be the representative, and I just mapped each element in the set to its representative. So now I can tell what all's in here by going through here and looking for the zeros, right? So I can reconstruct that set simply by looking for the zeros, if I ever wanted to do that, and I almost never do. Okay, was there a question? Did you have a question? Did you raise your hand? Okay. Like, flying around. Okay. All right, so the representation is clear. Let's talk about functionality. First of all, to make a set, all you have to do is you're going to initialize these things to all be in their own sets, and then you're going to build them up by taking unions. So that'll be more interesting in a minute, okay? Right now, we're going to assume that this collection of sets has been made and that this array is called R. And what I want to know is, how do I do the find of 4? What does my function do? What does find do here? It returns 0 because it just returned R of 4, right? We have it set up that way. Okay. But things get a little bit more interesting when what we want to do is start building up sets by taking unions. So what I want to ask is, what's our algorithm for taking the union of the find of 4 and the, the find of 07? What's our algorithm to do that? Okay, find of 4, I have 0. I know what's 0. I know this is 0, and I know this is 2. I know this is 0, and this is 2. So what's my algorithm? Yeah? Or an algorithm, I should say. Yeah? Okay. So I think you're suggesting something that's going to be useful later in the day, and what you're talking about is the size of them. But I want to change the data. I want to change this array in some way that afterward I can draw a different picture than this. Afterward, I can draw a picture that looks like this, where all of those have the same representative. So what's the algorithm? Any ideas? Yeah? Yeah, good. So all we're going to do is we're going to change the representative of this set to be the same as the representative of this set, okay? So keep that thought. My next thing I'm going to say is, or we could, and what's my or? What's the alternative to that? So I could change the 2's to 0's, or the 0's to 2's, either one. I don't care which, okay? So let's just choose. We're going to change the 2's to 0's. We can talk about the I don't care which in a minute if you want. Let's change the 2's to 0's so that all the things in this union have the same representative. How do I do that? Yeah? I do have to go through the entire array. That is correct. I have to go looking for 2's, right? I don't know where they are. I don't know where the 2's are in this this array of length 2 million, right? I got to go find them. Okay, and so that means I set up a for loop and I go, are you a 2? Are you a 2? Oh, you're a 2. I better change you to 0. Chunk, 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 0. What's the running time of that? That is big O of the size of the data, right? In the worst case, you have to go all the way through. Okay? Any question about that at all? So notice it doesn't matter whether I change 0's to 2's or 2's to 0's. I don't really care. I just need to know that all the things in the same set have the same representative so that so the comparison works. Okay, there was something else I wanted to say. Oh, I forgot to point out that, of course, find in this structure is constant time because it's just looking up an array. Okay? Any question about that? Is it good? Okay. It's also interesting to note that representatives do change over time, and so you have to query it every time you're interested in it. All right, fine. So as you can tell by this linear size here, there's room for improvement. So what I want to do is introduce a completely new data structure in support of this ADT, okay? This data structure is called a forest of up trees, okay? So finally, the trees grow up in our world, except they don't. They kind of like grow down, but they point up, okay? Well, kind of. Okay. Metaphors aside, here's how they work. A key is a root of a tree if its value, its array entry, is negative. Okay, so that's the indicator. That negative is just a flag. For now, our roots of the up trees are going to be -1. We'll be changing that later. Finally, and it's the most important part, that negative value indicates the representative of a set. Okay, so for example, in the first case, before we've changed anything, we have 4 sets, each with 1 element. Okay, and they are their own representatives. So for the find of 1 is 1. Find of 1 is 1 because 1's a root. 1 is a representative. Okay? Now, here's where it gets interesting. We need to take the union of, oh, I don't know, I'm going to do the 1 and, I don't know, I guess 2. I want to take the union of them. So I have these 2 up trees. Okay, here's 1, here's 2. All I'm going to do is put them in the same set by giving them the same root. And the way I'm going to do that is to point one to the other. All right? So which one did I do? I pointed 1 to 2, right? If I'm dancing in the right order here. I pointed 1 to 2. The way I indicate that in the array is to take 1 and make 2 its parent, like this. Okay, make 2 its parent. 2 is still a root, 3 is still a root, and 0 is still a root. So now if I'm drawing a picture of that set, I have 0, I have 2 and 1 points to it, and I have 3. How many sets do I have? 3 sets. What's the cardinality of the largest of those sets? 2, right? It's the size of this. And what does, so this is the hard one, what does the find of 1 return, do you think? That's right. How does it get there? Find walks up the tree, right? You do a find on 1, and you go, oh, you're not a root, but if you have 1, it's going to be here. Okay, and then you just walk up the tree till you find a negative value, and that's the representative. Yes? No, it doesn't right now. It will in 5 minutes, okay? All right. So are there any questions about that operation? Should we do another one just for fun, for kicks? Okay, so anybody want to give me a union to take here? So we should do union of, let's do find of 1 because that forces us to walk up. And 3, okay. Find of 1 and find of 3. Okay, so, and this was the first one, and I took the first one, pointed it to the other. Okay, so find of 1 walks up the tree. So now which tree is this arm? It's 2, right? And here's find of 3. So we're going to take 2 and point it to 3. Okay? So there is this walk up the tree to 2. Union is going to take 2 and point it to 3. And that's the only change that happens. Everything else is the same. Okay? Any question about it? So our forest now looks like 0, and then 3 is still a root, 2 points to it, and 1 points to it. Do you like this? It's kind of cool because it's new, but as our examples are showing, things can get kind of bad, right? You can imagine a sequence of unions that would just make this long, skinny tree an expensive find. So that's okay. You're supposed to feel that way. Any question about it? Any question about the mechanics of it? Is it clear? I need a vote for clarity. No questions? Fine. I want to keep going. All right. So here's a fancier representation here. Notice what we're doing. This is all kind of cool to me. I like it because there's one picture that we draw which we understand to be a collection of disjoint sets, right? The intersections are all empty. That's a collection of disjoint sets. There's one representative, which is another picture that we can draw, that is our conceptual notion of an uptree. And we can reason about the uptrees using this. It's the one that allows us to dance, right? But at the data level, this is how we implement it. So we actually represent those things just in a stupid old array because we love them. Okay? Now, I want you to internalize the connections between all 3 of these things by finding my mistake. So go ahead and take a look really quickly. I think it won't take you too long to come up with what mistake I made somewhere. There's an error. What is it? 3. Yeah? What should 3, if this picture is correct, what should 3 be? If this picture is correct, 3 should be a -1. If this picture is correct, what should 6 be? Yeah, so I just switched them, right? So 3 is the -1 and 6 points to 3. Okay? Any question about it? All right, so let's write some code. I think that's what's next. Oh, look at this. Oh my gosh. I have practically done MP 7.1 for you right now. Huh? Yeah, okay. So here's find. Look what find does. It effectively says, yo, are you the root? Right? It asks key I, are you the representative? By saying, is your element less than 0? If it is, then it gets returned. Otherwise, we just walk up the tree. This is walk up the tree. Okay? Any question about that? Okay. What does the running time of find depend on then? The size is not quite the right metric. It's close. The height, that's right. The running time depends on the height of the up tree. And in these up trees, we count height the same way we do in the normal dynamic trees. It's the path length from leaf to root. Okay? It's just you're walking backwards instead of forwards. Okay? All right, fine. So what's the worst case for these trees? What's the tallest they could be? Yeah. We can make a big long chain of them, right? Here's a harder question. One that takes a little bit of boldness to answer. What's an ideal tree? What's an ideal tree? Give me a big O for the height of an ideal tree. Yeah. Yeah? Yeah. Constant? We've never had a constant height tree before. But if you think about it, there's really nothing that precludes us in the description of this thing from doing this. There's a representative and everything else points to it. I like to think of it as an egotistical tree. Right? There's nothing that precludes us from doing that. You can write down what that definition would look like. Or what that example would look like. Okay? Go for it. All right, any questions about that? So all of a sudden, we have this little hope. We actually have a hope of a constant time function here. This is new for us. Okay? All right, but it's not clear. The path from here to there is a long way, let me tell you. All right, so this is our goal. This is our goal. I'm going to put a happy face by it. Okay? But we're not there yet. So what we need to do is talk about what we know right now for how union works. So keep in mind that I have here basically 2 roots of trees, and all I want to do is that. What does union do? It changes S. I was using S for the array name here. S of root 1 gets the value root 2. Okay? I have something to say about that for just a second. First of all, in MP7, we actually ask you to do the find first. So there's nothing about this function here that keeps you from doing stupid things. Okay? It assumes find has been called. In MP7, we say be sure to call find inside your function, inside your union function, so that you know you're operating on roots. The reason I don't do that here is I want to completely decouple the cost of find from the cost of union. Okay? So we understand that union has to happen on representatives. Okay? That's part of it. But the running time for actually making that change itself, apart from the find portion, is constant time. That's right. All right, any questions about all of that? Okay, but I'm still quite concerned about that worst case order n. we're still talking about this, and we had a naive implementation that already gave us order n. So we must be able to do better. And where I want to invite you to speculate on what we can do better is observing that if I have two trees, I can do this or I can do this, right? I always have that choice. I can choose a different representative. Now, my question for you is, if these are the two trees, which one should you do? Which one feels like a better choice and why? So you've got to choose to do this or choose to do this. So first or second. Raise your hand if you vote for first. Seems more reasonable. We're going to do this until everybody votes. So I don't care if it's a coin flip. I can filter those out. So, okay, raise your hands really high so I can see. Yeah? And if you think the other way is better? Okay, so kind of a coin flip, right? All right, let me ask you a question. How tall is the tree if I do, how tall is the tallest tree now? 2. How tall is the tree after I do this? Still 2. How long does find take? Proportional to the height of the tree, right? So I assert that doing this is better. I want to ask you another question, though. Okay, so in this example, yes, we should point 0 to the other one. I want to ask you another question, though, and that is, I'm going to do this. Which choice, this is a multi-clause sentence, okay? Which choice of either this or this increases find time for the fewest nodes? Okay? Which choice increases find time for the fewest nodes? This one increases find time for only 0, only one node, right? This one increases find time for how many nodes? 3 of them. That's a lot. That's increasing find time for almost everybody in your data set. So there's some argument that this 0 pointing to 1 is justified by that second question as well. All right, so those are metric-driven decisions, and in fact, they are the basis for 2 alternative strategies for taking unions, okay? One of them is called union by height, and its goal is to keep the overall height of the tree as small as possible. The other one is union by size, and its goal is to increase the find time, because distance to root is find time, for the fewest nodes, okay? All right, so let's focus on the first one for just a minute. I'm going to do something wrong, but you're going to let me do it anyway, and you're going to help me fix it. So see if you can tell what I'm doing wrong. So here's what I'm going to do. I'm going to, first die. Okay, I have it back. Can you see? Oh, there it is. Okay. All right, so I'm going to note that, look, 4 is a root and 7 is a root, but I recognize right now that I'm going to have to compare heights. So what I'm going to do is store an indication of their height along with that negative. So I'm going to use it as kind of an opportunity to give metadata to the algorithm, okay? So 4 is going to get value 3, and 7 is going to get value 2. And now my union, which already knows about those representatives, is going to go, okay, who's shorter? And the answer will be 7. And 7's value will get changed to 4. So the result of union by height will be to tuck that 7 right in there under the 4. Any question about it? What's wrong with it? What's wrong with it. Suppose there's another set out here. You got it? Really good. Yeah, that's kind of broken, right? So if I had, I guess I should do this, well, 42 is fine. If I had a whole bunch of these things and one of them had height 0, then the entry in the table would be -0 because it's a root, right? Well, that doesn't work. So what's the solution? We're just going to increase it by 1, right? It's height plus 1. So the roots store -h plus 1. So I was kind of lying all along. These are -4 and -3. And 4 ends up pointing to, 7 and does still end up pointing to 4. Okay? Any question about it? Okay, let's talk about the other one briefly. So this one is called union by size, and size here is measured by the number of nodes that a tree contains, and it increases the find time. So that's what distance to root is effectively for the fewest nodes. So we're going to point the smaller one to the larger one, yeah? Well, which one of them is smaller? 4. In terms of number of nodes, it's 4. Okay, so our ultimate goal is going to be to tuck 4 in under the 7 there, like this. And we're going to play the same game. 4 and 7 are both roots originally, so they're going to be negative. And now, though, instead of keeping track of the height, we use that cell entry as an opportunity to keep some metadata. And in this case, we keep the number of nodes. And in this instance, that is safe because we're never going to be dealing with an empty up tree. Up tree doesn't exist if it's empty. All right, now to point 4 to 7, we both have to adjust it and now change 7 to -12. So we have to change both of the elements. Any question about that at all? Okay, so what I want to know from you is, what do you hope I write here? So now we've been smart. One way or the other, we've been really smart about our choice of dance move, right? Of what points to what. What do you hope we gained from that? What would you like me to write here? Okay, both of these schemes for union guarantee that the height of the tree and thus find times is less than or equal to what? Do you think we can say a constant here? I don't think we can say a constant yet. It is big O of, usually I'm willing to write them down when I hear people kind of whispering it. I can't do constant yet. I can't do constant. It's not true. It's better. Linear is true, but it's not very good. Log n. Log n is what I want you to say. There. Yeah. Okay. Yeah. We're not going to prove this in this class, but we could do so. The argument is simply that effectively these strategies tend toward keeping things the same for each of the subtrees. There's a kind of balance, either in the height. If you notice, the height will only change when the two trees are the same height, and size. The smaller one always turns into something larger, okay? They're never more than twice. You never end up with something twice, a subtree twice as large as another subtree. So we now have, well, we'll look at the code in a second. Yeah? So then you can choose arbitrarily. Then it doesn't matter. So you can break ties arbitrarily. And in fact, it's interesting to note that it's when your two trees have the same height, so my right and my left have the same height, and I make one point to the other, that's actually the only time that a height will change, right? So in effect, you're working toward things having the same height, okay? All right, so this guarantees big O of log n height and thus find time. I want to talk about the code for that. Whoa. So notice that find hasn't changed at all. We didn't change a word of the text associated with the code for find, and yet we have done something that changed its running time. Okay? It's now big O of log n because we have bounded the height of the tree. But union by size, the union step gets more complex, right? Because we have to measure which one should point to the other. So how do we do that? Well, I'm doing union by size. Union by height actually requires some additional maintenance that I don't want to talk about here. There is actually a third opportunity for making a smart union called union by rank that is equally as efficient as union by size in terms of the record keeping, but it requires a new definition of rank. So, and I didn't want to do that today. So there's a third one. It also guarantees log n. I thought showing you one of the three should be adequate. All right, and I'm not going to test you about the other two unless I tell you how to do them. All right, so how does this work? Look, I know in union by size, my root is now going to contain the sum of the two roots. A new tree, it's going to contain all the nodes from one plus all the nodes from the other. So I'm going to add those together, and that's going to be my new root value. The fact that it's negative comes along for the ride, right? Negative plus negative is negative. All right. If root 1 is if root 1 is a representative of a set that's bigger than the other, then I'm going to do one kind of assignment. Otherwise, I'm going to do it the other way. That's it. That's all of the evaluation that I need. What's the running time of this function? Constant time. That's right. So this is big O of 1. So now we don't have constant and log n anymore. We don't have constant and linear for these functions anymore. We have constant and log n. So that's a marked improvement. But it isn't as good as I would like. In fact, there's one more thing that we're going to deploy. And I'm going to tell you about it in the last 30 seconds of the class, okay? Here's what we're going to do. We're going to do a find on 4, and as we navigate the height of the tree, we're going to redirect the roots, the parents of all of them, to be the result of find of 4. Okay? So, here's how it's going to go. I'm going to do a find on 4. I'm going to assume it has worked because when you're doing post-order processing on a recursive call, you can do that. I'm going to assume it has worked and redirect 4 to this and continue the search for 4's parent for 4's root at its parent. Okay? And then I'm going to do that recursively. I'm going to assume that the find of 2 has worked, redirect it, and then continue the search in 2's parent. I'm going to find on 7, redirect, continue the search, find on 9, redirect. And the resulting tree looks something like this. 10 is still the root, but it's got 9 and 2 and 7 and 4 and 11 as children. 9, 2, 7, 4, 11, and none of the rest of the structure has changed. 2 has still 3, 7 has 8, 4 has 5 and 6, and 11 is good. Now what's the height of this new tree? 2. Whoa. So next time, we're going to write the code that does this and provide the analysis. And what our fingers are crossed about, I almost want to do this for crossed fingers, is that we make constant height trees. Okay? All right, that's it. Bye.